Periodic motion, question 2. The diagram shows a car on a roller coaster. Important points are that it is initially at rest and is lifted to its highest point at position B, which is 35 meters above A. The total mass of the car and passengers is 550 kilograms, and it takes 25 seconds to lift it from A to B. It starts with negligible velocity and it moves unpowered along the track. This is a clue that you are simply thinking of conversions between kinetic and potential energy, and perhaps also there may be some lost energy due to work against friction. Calculate the power used lifting the car from A to B. So by definition, power is rate of doing work, or work done divided by time taken. The work done is equal to the gain in gravitational potential energy, which is given by mgh. So straightforward substitution of the values given in the question leads you to this answer. Finally, you should think about an appropriate number of significant figures. 2 of the values in the question were to 2 significant figures only. Therefore, 7,600 is an appropriate answer with the units given as watts. The mark scheme did allow also a 3 significant figure answer of 7,550. Next, the speed reached by the car at point C is 22 meters per second, and we're given the length of the track from B to the bottom of the first dip C as 63 meters. You're asked to calculate the average resistive force acting on the car during the descent. To get this right, you need to think about the big picture in terms of energy conversion. So if necessary, go back and look at the diagram and consider the journey from B to C. So at B, the car has got gravitational potential energy. This will be converted to kinetic energy at C. But the question has made it clear that you must also consider losses due to work against resistive forces. So to summarise that, you can put it all into one equation, that the potential energy at B is converted to both kinetic energy at C, but also some of it is converted to work done against friction. Rearranging that, you see that the work done is the difference between the initial potential energy and the final kinetic energy. We have got straightforward equations for each of those energy types, and then we can substitute all the values given in the question. If you do this a step at a time, you will get values consistent with 189 and 133 kilojoules, giving a difference of 56 kilojoules. So that's 56,000 joules, and to find the resistive force you need to consider what you know about work done. So work done is force times distance moved in the direction of the force, W equals Fx. So the resistive force must equal the work done divided by the distance moved in that direction. So that is the distance along the track. This leads you to an answer of 889 newtons. Note the question particularly stressed you must give your answer to an appropriate number of significant figures. This implies that there will be a separate marking point for getting that correct. So in this case, Since the least number of significant figures in the information given was 2, we would round this final answer to 890 newtons. If you were to look at the mark scheme for this question, it awarded separate marks for the individual potential energy calculation, kinetic energy calculation, the final answer achieved by this calculation here, and a mark for the correct number of significant figures. It is interesting to note, if you keep absolutely everything in the calculator, you will get an answer of 884.8. To 2 significant figures, that would in fact be 880 newtons. Strictly speaking, this is good practice, but mark schemes are sometimes written to make convenient interim marks that people can pick up even if they make perhaps a mistake towards the end. Explain why the resistive force is unlikely to remain constant as the car descends from B to C. Here you need to consider factors that would affect the size of a resistive force. So you may be able to make the point that air resistance increases with speed. Or alternatively, you could gain a mark by considering, in this case, due to the curved track, that the normal reaction is varying as the angle of the slope varies as the car moves from B to C. Either of these are worth a mark. However, there are 2 easier marks to pick up as well. One for saying that air resistance varies. I would say always say in what way when you can. In this case it would increase. And secondly, that the friction force varies or increases. Finally, this can now look like a circular motion question when we consider the car at C. So here we have a circular shaped section of the track. We're given the mass of a passenger, the reaction force and the speed. Drawing a sketch of this position C, you have the weight acting down and the normal reaction acting vertically upwards. We then need to consider the resultant force, which is the normal reaction take away the weight. We know that there is a centripetal force because the car and therefore the passenger are moving in this circular path. So there must be a resultant force in this direction which provides the centripetal force mv squared divided by r. So here the resultant force is r minus mg. Putting in the values and rearranging to find the radius gives an answer of 16.4 or 16 metres to 2 significant figures. 3 marks are allocated to this final part of the question. 1 was for the equation mv squared divided by r, and it is worth noting, if you had overlooked the weight and not included that in your calculation, you would get an answer of 12 metres, which was deemed to be worth 2 marks at this point.